All right, let's jump right in. Today, we're going to talk about a brand new kind of AI detective. It's built to solve one of the biggest, most frustrating mysteries in modern software, finding the real reason our apps break. It's called MicroRCA-Agent, and trust me, it's tackling a problem that drives engineers crazy and costs companies a ton of time and money.
You've been there, right? We all have. You're trying to get something done and the app you're using just dies. It freezes, it crashes, something goes wrong, and yeah, it's annoying for us, but for the engineers on the other side, oh man, their nightmare's just getting started.
Because the real question isn't just what broke, it's why it broke. And in today's super complex cloud applications, finding that one original sin, the root cause, is unbelievably hard. It's like trying to find a needle in a haystack that's literally made of other needles. And here's why it's gotten so much harder. See, back in the day, apps were mostly monolithic. Everything lived in one big code base. It wasn't exactly simple, but you could follow the trail of a bug. But today, most apps are built with microservices, a huge, sprawling web of tiny, interconnected services. A tiny failure in one corner can set off this crazy domino effect, and the original problem gets completely buried.
So this is where our new AI detective enters the scene. And the idea behind MicroRCA-Agent is actually super smart and kind of elegant. It doesn't just throw out the old rulebook. Instead, it combines the power of traditional machine learning with the incredible reasoning skills of large language models.
So here's the best way to think about it. It's a two-part detective agency. You've got your beat cops. That's the classic machine learning models. They're out on the street, pounding the pavement, finding clues, and flagging anything that looks remotely suspicious. And then you have the master detective in the office. That's the large language model. It takes all those clues and actually solves the case.
And this division of labor is just perfect. You see, classical machine learning is amazing at spotting patterns. It can sift through mountains of data and find the what, the things that are out of place. But it can't tell you why they're out of place. That's where the LLM comes in. It takes the what and gives you the why, connecting all the dots to build the full story. Okay, but before our AI Sherlock Holmes can do any brilliant deductions, it has to deal with a ridiculous amount of raw, messy data. I mean, a single failure can unleash a total flood of information, logs, traces, metrics. So the first job is to turn all that chaos into clean, usable evidence.
The system does this in 3 big steps. First, it goes to work on those giant, messy log files. Then, it analyzes something called traces, which are basically maps of how a request travels through all the different services. And finally, it boils down thousands of performance metrics. Let's break that down.
And yeah, this is what raw log data actually looks like. It's a mess, right? A jumble of error codes, unique IDs, super specific timestamps. For a person or even a normal computer program, trying to find a pattern in millions of these lines is basically impossible. It's just way too much noise.
To fix this, the system uses this really smart algorithm called drain. Think of it like a superpowered filter. It strips out all the stuff that changes every time, like the specific user IDs and timestamps, and creates this clean generic template. And boom! Instead of a million unique messages, you might only have a few core types of events. It keeps the meaning but gets rid of all the junk.
Next up, we've got the traces. And the system is clever here. It looks at them from 2 different angles. On one hand, a machine learning model is hunting for any unusual delays. Requests that are taking way longer than they should. And at the same time, it's also just scanning for the obvious stuff, like those dreaded HTTP 500 errors. So it gets a full picture of both the subtle slowdowns and the catastrophic failures.
And finally, the performance metrics. The thing is, a system is spitting out thousands of these. And during a failure, most of them are totally irrelevant. So the agent uses this smart statistical trick. It basically compares how the metrics look during the failure to how they look normally, and it only pays attention to the ones that change dramatically. Like here, it would instantly see that CPU usage went through the roof, but memory usage was fine, focusing its attention right where it needs to be.
All right, so all the evidence has been gathered, it's all been cleaned up. Now for the really cool part. All of these carefully prepared clues get handed over to our master detective, the LLM agent, for the final deduction, the grand finale.
So this is what the LLM gets to see. It's not a messy pile of data, it's a perfectly organized case file. It gets the clean log templates, it gets summaries of any weird behavior in the traces, and it gets a report on which metrics went totally haywire. It's all structured evidence, ready for analysis.
And this is absolutely key. The system doesn't just dump the data on the LLM and hope for the best. No way. It gives it a very specific set of instructions, a really carefully crafted prompt. It's basically told, you are an investigator. Your job is to connect these clues, figure out the chain of events, and build a logical explanation for why this all went down.
And the output, it's awesome. It's not more data, it's an actual answer. The LLM generates this final report that literally pinpoints the exact service that caused the problem, gives you a simple human-readable description of what went wrong, and even lists the evidence it used to make its call. It shows you its work.
Okay, so this all sounds amazing on paper, but does it actually work? Let's get to the proof, because the results are genuinely impressive, and they really do point to a huge change in how we manage these complicated systems. And here it is, the hard data. The system was put to the test in a major international AI competition, where it went head-to-head with a bunch of other state-of-the-art methods, and it performed incredibly well. This proves it's not just some cool lab experiment, it can hold its own in a real-world, high-stakes challenge.
Now this is my favorite part. The researchers did what's called an ablation study, where they tested the system by taking away one piece at a time. So take away the logs or the traces, and yeah, performance gets worse, just like you'd expect. But look what happens when they take away the LLM, the reasoning agent. Performance absolutely falls off a cliff. That's the smoking gun right there. Collecting the clues is important, but the AI detective's ability to reason, well, that's the real secret sauce. So to wrap it all up, the key strengths here are crystal clear. It flawlessly brings together 3 different kinds of data. It spits out results that actual humans can understand and use. Its design is modular, so you can actually use it in the real world. And, the big one, it brilliantly combines the raw power of machine learning for finding anomalies with the nuanced contextual reasoning of an LLM.
This whole thing leaves us with a pretty fascinating final thought. A system like this is a massive leap forward. It bridges that huge gap between just knowing there's a problem and actually understanding it. And it really makes you wonder, are we standing on the edge of a new era where our complex software can diagnose and maybe, just maybe, one day even heal themselves? It's a pretty powerful idea to chew on.